Solutions are what kind of matter? Give me a word for solutions. Ah, they don't all have to be liquids. They could be a solid, yes, but she says a solution is a combination of a solute and a solvent, which is true. Give me another one word or two words phrase. A solution is a blank. What is it? What kind of mixture? Homogeneous mixture. A solution is a homogeneous mixture. Okay, so a solution is a homogeneous mixture. We talked about two different types of mixtures early in the semester. What were they? Homogeneous and heterogeneous. Very good. Homogeneous and heterogeneous. Now what we are going to focus on are still homogeneous and heterogeneous mixtures, but we're going to come up with some fancy words for them. Let me give you a big picture of what we're doing for this next test material. So this is all test 4 material. Typically, just so you know, test 3 and test 4 are relatively high test overall, high test averages for most students. Test 1 is typically a high test average if you had high school chemistry and or you're really good at math and you got that dimensional analysis down pat. Lots of people, their residual knowledge carries them into test 1 and they do well. Test 2, we've talked about before, is a lot of times one of the lower tests. I think it's partly because of all the material and nomenclature. Nobody wants to learn ions. Test 3, usually a little higher. Test 4, also a little higher. Test 5, we're back down again. It's a huge amount of material. To give you that picture, why am I giving you that picture? Because if you're just kind of like, oh, I'll just halfway pay attention, I won't really pay attention. If you want to get your grade like boosted, you better really pay attention now. Okay? Because this is where you can boost your grade up a lot if you'll pay attention. We're going to go fast, but the amount of material is relatively a small amount of material, and so you've got, I think, for both test 3 and test 4, you have about like 4 days of lecture and then an exam. That's what we just went through kind of, and then it's the same thing again, about 4 days of lecture and an exam. Your exam, I think, is on Halloween.
No, the day after.
Day after Halloween? Okay, I knew it was somewhere around there. I saw the deadline for the homework. The deadline for the homework is Halloween. I'll say, so get your homework done before you go trick-or-treating, okay? So make sure you do that. All right, so what are we doing then? This whole section is a lot about solutions and liquids. That's what this whole section is a lot about. It's a lot about, we're going to be dealing with solutions, we're going to be dealing with electrolytes, we're going to be dealing with acids and bases. When I started teaching the Chemistry 109 class, or before I started teaching the Chemistry 109 class, I asked nurses, what do students need to know in a chemistry class that want to be nurses? And all of them said, oh, they need to understand acidosis and alkalosis. Of course, I was saying to myself, what's acidosis and alkalosis? Because I don't know. So, I had to learn. Interesting that that's probably this much of what you really need to know out of chemistry. Honestly, if you had to ask me, and I'm not a nurse, but if you ask me now, after teaching this class several years, this is from students coming back to me, what is the number one thing that a student gets out of chemistry class that they use? It's dimensional analysis. That's probably the number one thing. Secondly, I would say it's just an ability to think a little bit harder than you've thought before. Because I think some of you had high school classes that you kind of just floated through and you thought you were awesome because you made an A, but you really didn't work because you weren't expected to work. And so now you've worked hard and you earn your A or your B or even your C, but you earned it and you learned something. I think that's probably a great aspect of chemistry class, because I think you realize after you get through with it, that was hard, but I learned something in there, and then you can apply those thinking skills to some other classes. As far as acids and bases are concerned, are they important for nursing? Absolutely. Thankfully for me, you guys, when you take Anatomy 2, or if you've already taken Anatomy 2, you're going to have a whole section on that. How many of you had Anatomy 2? Great. See, you all are ahead of the game then. because I have the PowerPoints for one of the teachers that teaches that, and man, they dive in there deep. And so really it would have been nice had you had the chemistry before you took that class, but I think now that you've had that class, the chemistry will just kind of like reinforce, and you'll be like, oh yeah, I remember that. So it'll be good. So you're about almost half and half, it looked like, that have had that. So the rest of you, you'll see it in that anatomy class. All right, let's get started. A solution, as I've already said, is a homogeneous mixture. A solution is a homogeneous mixture that contains small particles, very small. It's a homogeneous mixture that contains small particles. It may be in gas, solid, or liquid state. It could be in any of those states. And a gas or a liquid solution will be transparent, meaning you can see through it. So gas and liquid solutions will be transparent. A solute in the solution is the substance, what? Being dissolved. Good job. It's the substance being dissolved. What's the solvent? Doing the dissolving. Substance doing the dissolving. Now, typically, the solute is present in the smaller amount, and the solvent is typically present in what? The larger amount. Now, that's not always true, but most of the time. The 8 o'clock class had trouble telling me some solutions. Can you give me some solutions? Say it again. Somebody said, what was the loud thing? Water. I wanted somebody to say that. I heard that, and I wanted somebody to make sure they said that. The water that you and I drink should be a solution. You should not be drinking pure deionized distilled water. You need to drink water with ions in it, with stuff in it. So the water we drink is a solution. Now, I heard some other things. Salt water. How many of you have contacts and use saline solution? Is that a solution? Solution of salt and water. In that saline solution, what's the solute? Sodium chloride. What's the solvent? Water. Does that make sense? So anytime you think of a solution, start thinking, what's the solute, what's the solvent? Just kind of think through that. So let's take another one. Sweet tea. Sugar is one of the solutes. Tea extract is also a solute. And then what's the solvent? The water's the solvent. The water's the solvent. Good. What about coffee? Black coffee for sure. What's black coffee? The grounds or the coffee grinds, I guess that is what you call ground coffee, or your coffee beans that then you grind. That's what's dissolved in the water. So that's the solute, the water's the solvent. Is it a solution? Yes. If you even add sugar to it, is it still a solution? Yes. Now if you add cream to it, it's a different thing. And that's what we're going to get to. Colloid. A colloid. A colloid is still a homogeneous mixture. It's still a homogeneous mixture that contains larger particles. Now when I say larger, I'm meaning larger than a solution, okay? So relative to each other here. So a colloid is a homogeneous mixture that contains larger particles. It often has an opaque appearance. It often has an opaque appearance, meaning you can't see through it. It's cloudy. Maybe you could put cloudy there, that might help you. Colloids are pretty unique in that they can exhibit what we call the Tyndall effect. And that is when light is passed through a colloid, the light beam is seen. So a colloid is a homogeneous mixture that contains larger particles. It often has an opaque or cloudy appearance. Colloids can exhibit the Tyndall effect, and that is when light is passed through a colloid, the light beam is seen. Now, I'm going to try to show you something. I wasn't able to show the morning class this. The camera in here is maybe a little different. I'm going to try. Give me an example outside where you have seen a colloid and the Tyndall effect. Can anybody tell me? Can you give me any examples of colloids? Natural colloids. Say it. Thank you. Fog. That's exactly right. Fog. Fog is a colloid. Do you know what the Tyndall effect is? When I talk about fog, where have you seen it? Say it. Car headlights. Have you ever driven in fog and you saw those beams shining through the fog? You saw that like light beam shining through the fog? Or maybe a concert. Nobody said that. I don't know if you'll, actually you can. Well, no, you can't. Let me see if you can. I can see it on this screen real well. Yeah, you can. It's much better than this morning. This is one of my morning views. In the morning when I go out and early, which is every morning, but some days I get this. And what happens is in the morning when it's foggy, and I've seen this more than once, but I just happened to take a picture of it this morning, or not today, but the morning I took this. But what happened was I was walking out and it was really foggy and the sun was coming up, and when the sun was shining through the branches of that tree, you saw those beams. And I thought it was pretty, and then I also did remember I could use that for the Tyndall effect. So, what happened to it? Oh, my phone's dying. It's time to be done. Okay. Anyway, get up early one morning and you might see that. Pretty neat though. So some examples. Let's put some examples on here. Fog. Now, do you remember what I said about that coffee? When you put the cream in it, it made a colloid. So could you say that milk or cream are colloids? They are. Yep. Milk is a colloid. Mayonnaise, that's a colloid. Salad dressing, Miracle Whip, that's what I'm talking about there. Those are colloids. Foams. Foams are colloids. Foams are colloids. So all of those are colloids, meaning they're homogeneous mixtures of the same throughout, but you can't see through them. Does that make sense? Because they're small, or they're larger particles. How many of you take whipped cream and just squirt it in your mouth? You're eating a colloid. So sounds gross when you say it that way, but that's what you got. All right, so suspensions. What are suspensions? Suspensions are heterogeneous mixtures that contain large particles that settle with time. They're a heterogeneous mixture that contains large particles that settle with time. And the particles could be filtered or centrifuged. The particles could be filtered or centrifuged. This is pretty important for you that are going to be nurses, because tell me about a medication that is a suspension.
Yeah, it goes from like a solid, like a little mixture and water and you
Do you work at a pharmacy? Mm-hmm. And tell me what medication that is. For who, usually?
People who can't really like swallow like capsules or tablets.
And who are those typically? Who? Children. Do you remember that pink bubblegum amoxicillin medicine? That was a suspension. Isn't that funny how you all are like, ugh. You remember that, don't you? It looks like Pepto-Bismol, but she may have gotten grapes. She had a nicer pharmacist than you did. She went to Kroger, you went to Walmart. I'm teasing you. So that is a suspension. That's a suspension. Now, suspension medications, and this is my own little jingle, must be, what do you think I'm going to say? Thank you. Shaken before taken? That should be like on a shirt. Shake before you take. You need to add that to the pharmacy. Where do you work? Which pharmacy? Oh, now she works at Medicine Arts. They do all kinds of flavors there. It's because it's arts. Okay? So, you all need to have a little fancy sign that says shake before you take. And then a little person shaking. See, wouldn't that be fun? All right, why do I even mention this to you and make it a big deal? Because, guys, what are you going to be, some of you? Is that important? Now, let me throw something else out at you. And you guys, honestly, this is the first semester, or not the first semester, let me rephrase that. This is the first semester that I have had as many students who are Bosnian refugee descendants, I guess is the right way to say it. I'm not sure if that's the right way to say it or not. But when I was teaching at Bowling Green High, that's when all of the students started coming in from Bosnia because there was all the war going on. And that was 20 years ago. And so this generation now that's coming to college are those kids that were born here. But you all that are in that realm, some of you, you know who you are, and there's nothing at all wrong with that. I'm just using that as an example. Bowling Green is a melting pot of a lot of nationalities. I have noticed last names have changed so much when I started teaching compared to now. I mean, it's really amazing, the last names that I see now. I mean, if you heard me, I don't even think I called roll, did I? Because I don't want to try to call roll, because I can't say all those names. You guys are blessed with all this heritage and all this cultural knowledge that I don't have. And so That's great for a lot of reasons, but it's not good for somebody like me who knows English and English and moo or, goat language or something. I don't know anything else. And some of you are like me. You don't know anything else. So here's what we have going on. We've got mama or daddy who have sick little kid. You're going to be that nurse who has to explain to mama and daddy who are worried to death about sick little child, and they're going to sit there and shake their head and act like they understand, but they do not comprehend. So what do? You got one handy? Sure, let me pull one out of my back pocket. Oh, I bet you have an app for that, don't you? You probably do, and that'd be good. That's a good thing about a phone. But the point is, here's my problem that I have, and since you work at the pharmacy, I want you to address this with the pharmacist. The bottles that amoxicillin comes in, tell me about what they look like. Red? Can you see through them very well? Mm-mm. Or they might be that brown bottle, or they might be that one that looks like the milk jug. Can you see through it? Can you tell when it's shaken up and when it's not shaken up? No. Why don't they make a bottle that's clear? I understand you put a sticker on it. I can't read English. Do you see my point? Why?
There's a picture next to it on our labels.
Wait, are you asking why they make the
Why do they make the bottle where you can't see that it's not shaken up?
because of the light?
I'm sure there is too. I'm just asking. I'm being devil's advocate. I'm sure it's probably to do with the light. But it's supposed to be in the refrigerator. Is the light stay on when the refrigerator door is closed? Are you sure?
Yeah, I've tried.
Have you been in there? Yeah.
I played with it. I would get right in there just to make sure it goes on.
The point is, guys, it's your job as that nurse to be able to explain to the people what? You have to shake this. You have to be able to explain that somehow. So that's one of your little thoughts. Now, right now, you're thinking, she's crazy. I'm not ever going to work with pediatrics because I can't stand kids. But you know what? It could be the older person. That insulin has to be shaken. I did not know that.
Can that you get, in the center, it has all the medicine. It'll separate, be white, and it'll be clear. And you have to shake it and you have to refrigerate it before you take it.
Interesting. I did not know that. Thank you.
Not the valve, but you have to flick it. Not those. You have to pour your own. This is where it's come pre-packaged.
Interesting. Well, there you go. That is a good reason then. So somehow you've got to be able to explain that to people. And that's your job. Mine's just to teach you chemistry and tell you have to explain it to people. But that's something I think it would be hard. I'll tell you what I would do if I were a nurse. If I were a pediatric nurse, which I would do, this is what I think I would do. I would get a little bottle that is clear and either get some old medicine or something and show so they could see it. And I don't understand why a pharmacist doesn't do that. I understand the reason for the light and all that, but why can't they do that? You work at the pharmacy. It's your fault. No. And wouldn't that be good, though, if they could do that so they could show people? And maybe it's not a big deal, but I bet there's a lot of kids who don't get their medicine right because people don't shake it. What do y'all think? I think there probably are. You don't know. Well, you're alive today, so we think she probably did. She probably did. All right, so interesting, but make sure you put that little note up. Shake before you take. All right, so classify the following. This little chart over here, the table is just some basically it's the same thing I've already written in a short form. Cherry Garcia ice cream, if you don't know what that is, which I didn't either till I looked it up, but it's like cherries and chocolate and vanilla ice cream. So what would that be? Of the three words we've talked about, suspension, colloid, or solution? It'd be a suspension. So Cherry Garcia ice cream would be a suspension. What's mayonnaise? Say it again. All right. What's seltzer water? Now, I would argue with somebody on seltzer water probably. So we'll never give you something like seltzer water. But what do you all want to call it? Bubbly water. What would you call it? Some of you call it a solution.
If it's cloudy enough.
if it's got enough gas dissolved, or it's one of those ifs. I won't give you one like seltzer water. I'm not even going to put it, because you could argue all day long that it's a homogeneous or heterogeneous solution, not a solution. You could argue. Put your phones up, guys. Please put your phones up all the way up. Put them up all the way. Okay? Nail polish. What do you have to do with nail polish? Shake it. So what is it? It's a suspension. Nail polish is a suspension. What's Gatorade? Solution. What's brass? It's not. It's not a liquid. You're right. What is it? It's a solution. Now, there was a time in the past where I talked about brass. Does anybody know what special kind of mixture brass is? Starts with an A. Say it again. Say it louder. Thank you. Alloy. Do you remember that? Go back up, and I didn't point it out tonight, but look what this says again. Read what this says again. Maybe gas, solid or liquid. What do we typically think of as solutions being? That's not true, though. That's not the only solution that there is. What's in this room that you're breathing? What is air? A solution. It's a solution of gases. So a solution can be a solid, and brass is a solution because it's a solid of metals mixed together. Jewelry, we went through this whole deal with alloys before. All of those are solutions. Nail polish remover. It's a solution. Hand cream, that means like lotions. Colloid, good. Calpectate, it's a diarrhea medicine. Melanta would be suspension, has to be shaken, good. Has to be shaken, good. Be sure that you can kind of classify some different things. Yes?
Okay, so for the solution, you said that it's transparent, but you said coffee and tea are part of that. I can't really see through those.
Well, let me tell you, think about if you thinned them down, if you diluted them enough, could you see through them? Or if you had a strong enough light, could you see through them? Can you, like, for instance, give you an example. If you got them thin enough, you could see through them. If you had a tube, even of really strong coffee, if you had a thin tube of it, could you see through it? Yes. Our problem when we're thinking of that, and you're right, our problem is we're thinking of a cup that's probably already opaque itself. In other words, you can't see through that cup either, so there's no light getting through it. So when we pour it in there, it just looks like black. And you think, well, I can't see through that. But take it and put it in a clear, colorless glass, or thin it up. You know, if you had some kind of container that was real thin, then you could.
Coffee pot, like when you're looking through the
That's
coffee
true
pot.
if the light's shining through it, depending on what kind of coffee pot you've got. If you've got a, depends on how strong you make your coffee too. I mean, it really makes a difference. If you had some really, really strong coffee, so it would make a difference. Tea, is that, you said coffee and tea? Same thing. Yeah, same thing. All right, an electrolyte. What is an electrolyte? An electrolyte is a substance that conducts an electric current when it is dissolved in water. It's a substance that conducts an electric current when dissolved in water. What are some things that you know that conduct an electric current when they're dissolved in water? Say it again. Salt? Yep. Sodium chloride? Have any of you had a teacher, a chemistry teacher, or you've had a class where they would test the conductivity of a solution? They might have had like a probe and a light bulb, and they would stick it in there, and if it glowed really brightly, they said that's a strong electrolyte. If it was a weak then it would be a weak electrolyte. Or have you ever had a teacher who ran, or maybe you did a science experiment where you ran a clock on orange juice or on salt water or on a potato? Have you ever seen those things done where they'll just stick the probes in and you have a battery basically? That is because that's an electrolyte. That's why that works. It's because those electrons and protons, those ions in other words, have dissociated, meaning separated, and they're able to transfer that current. That's why you're seeing that. And I basically explained a strong electrolyte. A strong electrolyte dissociates or ionizes completely when dissolved in water. It dissociates or ionizes completely when dissolved in water. For example, sodium chloride, the one we've just talked about, dissociates into sodium ion and chloride ion. So it dissociates or ionizes completely when dissolved in water. Now, before we talk about weak electrolytes, I want to talk about electrolytes with people for a minute. I don't know of any of you, and you may be, but I don't have an athlete review I have to complete on any of you. So that's why I'm saying I don't know. In my other class, I do. I have 2 football players. I don't know if any of you are hardcore athletes. You may be. I don't know. So I'm going to assume not, but that doesn't mean you aren't, okay? If you are a hardcore athlete, let's take a football player. And not even a football player all the time. I'm talking football player in the middle of the summer when they are getting ready for the fall season. Tell me they're working out lots of times in the heat. What's going on? They're sweating a lot. Now, and the guys that are in my class at 8 o'clock, we were talking about this morning, and I wanted their confirmation. So I said to them, I'm like, okay, guys, they only give you Gatorade, or do they tell you to drink water also? And they're like, oh, water. And then they will give us Gatorade, but they're the ones who give it to us. It's like we don't go get it ourselves. They tell us what we're going to have, and this is what they hand us, and that's what we do. But what's number one? Water. The problems are marketing. That's not the marketing problem. That's our problem. We believe the marketing. The marketing says, what do we need? We need Gatorade. You need electrolytes. Oh, you've got to have that. Guys, the majority of us don't. The majority of us do not. Now, do those football players on that hot summer day, they're losing a lot of salt through sweating? Chances are, do they probably, in the middle of that, need some electrolytes? Yes. Depends on how long their practice is. Are they going to eat before? Are they going to eat afterwards? Yes. Are they going to drink a lot of water? Yes. What's number one? Water. That's number one. Most of us that are somewhat active or quite active, however you want to say it, most of us can handle not ever having a Gatorade. Because what are we doing? We're eating well, we're drinking water, and we're in balance. If you overconsume salt, chances are you're just going to urinate it out. The problem with Gatorade, what is it? It's not the salt so much as the sugar. What is Gatorade really? A lot of sugar. And most of us don't worry about the extra. We don't need the salt, so what are we doing by drinking Gatorade? We're just drinking sugar water. You might as well drink a Coke, or you might as well drink Kool-Aid. It's probably not any different, really. Unless you just really like Gatorade, and that's fine. And I don't know that Gatorade has as much sugar as Coke's probably, but it's still, most of us don't need it. Now, the class this morning was saying, well, what about smart water? Should we drink smart water then? And I'm like, no, don't waste your money. Just drink water and you eat. Now, what if you're just eating junk all the time? That possibly, but chances are if you're eating junk, you're eating a lot of chips. So you probably have enough salt. So you probably still don't need it. So does that make sense? So much of what we think we hear in the media, oh, you got to make sure you got enough electrolytes. Most of us don't need that much more. We already get enough. If you have a decent diet, it's water you need probably. Most of the time we're dehydrated. Now, if it makes you drink to have something in your water, I guess then go ahead. But you're probably getting a lot of extra calories you don't need too for some of us. Now, some of you need them, so it's up to you. Weak before I go to weak electrolytes, there is a group though. I want to address this. There is a group, 2 groups. Which groups or when do folks have trouble with electrolyte imbalances? Say it. Females? Give me an example. That's not where I'm thinking, but you might know more than I know. Go ahead. You're thinking iron. That's not called an electrolyte, although it is a metal, but it's not called an electrolyte. You are correct. Females need more iron. Men can actually overdose on iron. Women typically don't. Populations of people. We've already talked about one group. Who? Kids. When would kids need electrolytes? Doing what? Throwing up and diarrhea. Because what's happening? They're dehydrating, but not only do they need the fluid, chances are if they're throwing up, they haven't had anything to eat, right? And or if they have diarrhea, they can't keep anything in long enough to break it down. And so what's happening is they are continually getting rid of any possible electrolyte. That's when the Pedialyte, that is when that would be needed. That definitely is when that would be needed. Go the other age, opposite. Tell me, anybody work in a nursing home? Say it again. Used to? Tell me what you know about a nursing home. The residents in a nursing home, what 2 ions do they get low on? Do you know? Do you remember those? Anybody know? What did you say? Potassium and sodium. Elderly have a lot of trouble with maintaining, some, not all elderly, but a lot of elderly folks have trouble maintaining their sodium and potassium levels. Typically, you think of people who are not in the best of health, they can't get around. Are they eating as much? Not usually. Many of them have high blood pressure. So they're on a diuretic, which means it just flushes all the fluid out of them, which flushes all of the ions out of them. Because are these water soluble? Yes. So then what happens? Who's worked in a nursing home before? Several of you probably have. All right. How many of you have had a patient who they were fine yesterday, today you go in and like they are so weak and they are definitely not thinking straight? You ever had that happen? And then they go check their sodium levels or their potassium levels and something's out of whack. That's almost always what's happened. My mom has had low sodium. She has struggled with that in the past more than now. She had, knock on wood, she hadn't had it recently, but in the past she has had both low sodium and low potassium. She could be fine, and then a day later you're like, this is what we do to my mom now. If she's not thinking straight, because she's usually pretty good, but if she's like getting a little off, we're like, have you had your sodium checked lately? We just ask her that. If she gets really, really weak, which she again hasn't done, but now because we've gone through this so many times with her, it's like we know if she's getting weak, it's like go get your sodium checked. Because we know something's going on. Interesting, with her situation, she does have high blood pressure, so she's on the diuretic, but they finally figured out with her situation what had happened was she had had some mini strokes, and her brain, instead of saying, hey, you need sodium, her brain was actually telling her, you've got enough sodium, flush it out, even when she didn't have enough sodium. So her brain, the mechanism was messed up. Somehow, I don't know how, it's kind of gotten better now. But anyway, it's really interesting. Did anybody have a story on that where they had that happen and then after they got their sodium and potassium up, they were like back to normal? Have y'all seen that in the nursing home? They've worked in the nursing home like that? Yeah. It's pretty interesting. So again, if you have, I know your parents aren't that old, but if you have grandparents that you see that happening in, you might just mention, have you checked their sodium and potassium? Because it's very likely that could be what's going on. So it's kind of interesting. All right, what do the sodium and potassium do in our, why do we need those? Do you know? What is our main solvent base in our body? Water. Do we conduct electricity? Yes, we do. Have you all ever had those toys? The one I can think of right off the top of my head is the little chicks at Easter. Have you ever had those little chicks that you set on your fingers and they chirp, 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 chirp? Nobody knows what I'm talking about. You never seen those? They have little metal on the bottom of them, and you sit them on your finger? You've never seen those? A few of you? Yeah, they sell them at Kroger. They sell them. Not a real chick. Not a real chick. Not a real chick. Wake your friend up. She's going to fall in the chair there. Is your sodium low? So, because you know what I'm talking about? The fake chicks. The fake chicks with the little metal pieces on the bottom, and you put them on your finger and they chirp. How do they chirp on your finger? You can also set them on a piece of metal, and they'll do the same thing. Why? Because we conduct electricity. That's why. They have a battery in them, and when you connect the circuit, you are creating enough connection. They can pass the ions through you, and then, or the electrons through you, and you're making that work. Tell me what makes your heart beat properly. Basically, the potassium is what's the ions. Your brain, what's going on with your brain? Is it this whole electrical thing? I have not seen the entire movie Inside Out, but that's really kind of a funny movie. Because when you think about it, your body's all inside of you. It's all this stuff. And I mean, I know that's like mood stuff, but same thing. But all of this inside of you, is there electricity? Are there circuits? Are there lights going on in a sense? I mean, is there this pathway of electronics going on in you? Yes. So when those ions are not present in the concentrations they need to be, are those circuits going to be not working right? Just like you can have a short in an electrical line. Same thing. Same thing in you. Weak electrolytes. Weak electrolytes dissolve in water to yield unchanged molecules with a few ions. Dissolve in water to yield unchanged molecules with a few ions. And let me give you a common example of this, or several, but one of the examples is acetic acid. Acetic acid. That's the formula for acetic acid. Acetic acid dissociates into some hydrogen ion and acetate ion. But most doesn't dissociate when dissolved. Meaning it stays just like that. So you do get some ions, but most of it stays as the acetic acid molecule. Tell me about the light bulb if we were sticking the light bulb to test the conductivity of a weak electrolyte compared to a strong electrolyte. The strong electrolyte would be what? The light bulb. Bright. The weak electrolyte would be what? Dim, but still glowing. Does that make sense? Because there aren't as many. Is that the same thing? And this is my point to get you to realize about people. When there aren't enough ions Are they weak? You follow me? What's going on? Does that make sense? That's why that dramatic, for those of you that have seen this in the elderly, that's why the dramatic boom, when you get them the sodium and potassium that they need, it's like they're like a totally different person compared to when they don't have enough. That's why, because you've got to have those to make the brain work. You've got to have those. And the heart, All right, the last comment on electrolytes is the non-electrolyte, and I think that's a pretty self-explanatory. Non-electrolyte is a substance that doesn't conduct electricity. A substance that doesn't conduct electricity. When dissolved, it exists as a molecule. When dissolved, it exists as a molecule. Make this easy for yourself. Molecular compounds are non-electrolytes. Molecular compounds are non-electrolytes. I am not going to ask you to tell me if something is a strong or weak electrolyte. Not right now. I will not ask you that. What I will ask you, though, is it an electrolyte or is it non-electrolyte? How are you going to know? What are you looking for to say this is an electrolyte? A metal. That's exactly right. You're looking for an ionic compound. What are you looking for to say this is a non-electrolyte? Which is all what? All nonmetals? So tell me these examples then. Potassium chloride in water, what would that be? That's an electrolyte. That's an electrolyte. Sucrose is C12H22O11. C12H22O11. That's what sucrose is. What would that be? Non-electrolyte. Now, does sugar dissolve in water? Sure it does, but it doesn't conduct electricity. Potassium iodide in water. What is it? Electrolyte or non? It's an electrolyte. One last thing that you learned when you were a kid. Why do you not let the electronic devices that are plugged in fall into the bathtub? What did you say?
I said, boy. I did that as a kid.
You did that as a kid?
I threw it in there.
You weren't in there though.
Oh, no, I'm good.
So tell us what happened. She had vivid memories. Did you see that reaction? She was like, whoa, I remember that. I hadn't thought about that in years. What happened?
Like the whole bathtub just kind of like.
Popped?
Yeah.
Sizzled?
Then I got popped and sizzled.
That's the best story ever. Nobody's ever told me they did that. That's awesome. I'm glad you're okay. I'm glad you weren't in the bathtub. Or the little brother or sister in the bathtub. We're glad they weren't in there either. That's hilarious. What did you throw in there?
It was one of my toys. It was something like I just like one of those like little video game, like the little GameCube video.
And it was plugged in?
Yeah, and I plugged it in where like the hair dryer goes.
Uh-huh.
And I just kind of was like,
Woo!
it was my older brother. So like,
Ah, that's the story. Get rid of that thing. That's hilarious. Well, there we go. So, does water conduct electricity? Yes. Now then, pure water. Pure water. Does pure water conduct electricity? No. What is pure water? What kind of compound? It's a molecular compound. Pure water is a molecular compound. So why did her water conduct electricity? What have y'all told me the water is that we drink and that we fill up the bathtub with? It's a solution. Does it have ions in it? Yes. So Pure water does not conduct electricity, but normal water does conduct electricity. A lake is definitely going to conduct electricity because it's got all kinds of dissolved substances in it. And many of those are ions. So yes, a lake would conduct electricity. Guys, that is why you hear people say, if you, first of all, you don't drive through or walk through flooded areas. And if you see a power line down, you don't ever get near that. Stay in your car if you see a power line down and go the other way. Why? I'm talking down on water. Why? Because you can get electrocuted. Because that water is going to conduct electricity. If you've got a puddle of water and there's a power line, you're going to get electrocuted. Now, to give you another example, and I'd forgotten about this until today, basically, to use it with this. Electric fences. Any of you been shocked by an electric fence? Some of you have. When there are really, depending on the charger, electric fences put out a certain amount of electricity depending on what charger they're connected to. But some chargers you are not going to be hurt that much by unless you're wet. Give you a scenario. I had tapped our electric fence that we used to have, and it hadn't been a big deal. One day, though, I was near it, and I was hot, and I stepped down and bent over, and all of a sudden I found myself like I just came up off the ground. I'm like, why am I on the ground? I had touched it with my wet forehead, and it knocked me to the ground. That's how much electricity we can conduct, whereas if I had just hit it with a dry part of my body, it would not have been nearly the same. And it was because of the wetness that caused it to be so much stronger. So electricity and water don't mix. You don't mix them. So that's a great. I wish I had you to explain. In that same, I don't know if, I'm hoping that got on the video because that was too good. I don't know if it got your sound though, but that was too good. So I've never had a student that had that happen. All right, equivalence. What is an equivalent? I'm going to tell you right now, equivalence, I had never used equivalence ever in chemistry. It's pretty much a medical thing. And I'm going to show you tonight where you're going to see this in just a minute. But what is the term? An equivalent is a unit. It's a unit. And it's a unit used to express the amount of each ion in a solution. So it's a unit that's used to express the amount of each ion in a solution. And it relates the amount of an ion to its charge. It relates the amount of an ion to its charge. Here's the key though. The number of equivalents per mole of an ion is equal to the charge of the ion. So if I ask you how many equivalents per mole are there, you just say what's the charge? But really you're supposed to know the charge. Hence the reason we learn charges of ions. So if I said to you sulfate, first tell me what the charge is. -2. So it has how many equivalents per mole? 2 equivalents per mole. Don't make this hard, okay? Don't make this hard. The amount of an electrolyte in blood plasma and IV solutions is often reported in the number of milliequivalents per liter of solution. And 1,000 milliequivalents is equal to 1 equivalent. Let me show you what we're talking about, and then we'll look at these examples. So, lactated Ringer's solution. Anybody heard of that before? I'm curious, do I have anybody actually in the nursing program? I don't think, I mean, you're already in it. Just got accepted, but anybody actually in the program right now? I didn't think anybody in this class was. Okay. All right, this is a solution. I love it when I have students who actually are in it because they've lots of times had a lot of this already and they can tell me a lot, which is cool. But lactated Ringer's solution is a common solution that's used in basic situations of just outpatient surgeries, which is where this one came from, diagnostic testing, anytime where they have to give maybe some medicine to put you under, or just want to make sure they have you opened, they have a shunt in you, or that's probably not the right word. What's the right word? Just where they have an IV in you to put stuff in if they needed to. That's like not the best way to say all that. You know what I'm talking about. This is lots of times what they'll use. So if you look at this bag, this is telling us what's in this bag. And what are some things you see here that are what we've talked about? You see some, obviously you see some words that we've talked about. So sodium chloride. You see potassium chloride, calcium chloride, pH, and then we'll keep going. You see electrolytes, and you see water, and you see sodium, 130 milliequivalents. Keep going. Chloride, potassium, calcium. Do you see all that? So here's what's happening. This bag is how much? What's the volume of this bag? Which is what? A liter. And what did we just say that many times they're expressed in? Milliequivalents per liter. So is this milliequivalents per liter? That's what they're saying. So they're saying that this bag contains 130 milliequivalents per liter, 4 milliequivalents of potassium, 3 milliequivalents of calcium, and 109 milliequivalents of chloride and 28 milliequivalents of lactate. Now, at this point, you don't know what lactate is, and I will tell you, in general, it's a carbon-based ion. So think oxalate, acetate, think those are carbon-based. That lactate is similar to that. It's carbon and oxygen. I don't know the formula off the top of my head. It's not one I have memorized. But that tells us, if you go to our next statement in our notes, and I'll come back to this, read the next sentence. What's it say? The positives have to equal what? The negatives. And it gives you the example, if you have a solution of potassium chloride and you have 40 milliequivalents of potassium, then you've got to have 40 milliequivalents of chloride. Now, go back to the bag. And like I said, even if you don't know what lactate is, add up your positives. Sodium, 130. What else is positive? Potassium, 4, that's 134. Calcium, is it positive? So 137 total positives, do you see that? Are you following what I'm saying? 137 total milliequivalents that are positive, yes? It shows you chloride, and you know chloride's negative, and you're like, but there's only 109 negatives. Now put 109 with the 28. What do you get? 137. So that tells you that lactate is what? Negative. Follow what I'm saying? Because the positives have to equal the negatives. So you can kind of, just by knowing the positives have to equal the negatives, you can figure out lactate has to be negative. And it's balanced. It had to be balanced. Had to be balanced. So you should be able to then I'm actually going to do this problem first. Do the second problem first based on what we just did. It says the solution contains the following ions, sodium, potassium, and calcium. And it tells you chloride is the only anion present what is the concentration? How are you going to figure that out? What do? You add them up. Think about it, guys. If chloride is the only ion present, then how much chloride does there have to be there to balance out all those positives? The same number of positives that are there. Yes? Don't make this one hard. So you've got the 15 milliequivalents per liter, that's the sodium, plus the 10 milliequivalents per liter, that's the potassium, plus the 4 milliequivalents per liter, that's the calcium. What's that equal? 29 milliequivalents per liter of chloride. That's how many you would need, because this equals the total positive, and that has to equal the total negative. Now you probably want to write yourself a note there. I did a little short by just putting the positive, but you might want to write yourself a note to remind, or better yet, you could even just draw an arrow and say, hey, look up there, that comment tells me what to do. And hopefully you'll see that. The problem above this one, could you have done the problem above this if you didn't know anything about milliequivalents or equivalents? This problem. You should. Why? What is it? Is it dimensional analysis? Straight up, dimensional analysis. Do it. Straight up. It's all right there for you. So do that problem. What's the given? Put the wrong thing there, didn't I? Getting ahead of myself. Yes or no? What do you get for your answer? How many significant digits? 3. So what's your answer? Say it again. I'm hearing 1,000. Shouldn't be 1,000. I'm hearing 1,000? 123. You should get, do it again. Should get 123 milliequivalents. Question, go ahead.
Could you repeat what you're getting for 154 milliequivalents of Na? I thought it was just the charge.
No. If the charge, okay, let's go back up to this. Go back up to this. If we are straight up just talking about, let's say we're talking about an entire mole of sodium. So we're talking about 22.99 grams of sodium. Then we say we have a whole equivalent of sodium. Here we don't have a whole mole of sodium. We have a solution of sodium, and the concentration, which is really goofy here, in essence, the concentration is given to us in milliequivalents per liter. Lot of time, and this is kind of that's a really good question, because I haven't, the next Monday we're going to talk about how to measure concentration, but you know this already. Percentages, a lot of times percentages are used for concentration. Give you an example. If you're out and about, look on a rubbing alcohol bottle and you will see it may say 70% or 90%. That means if you had 100 milliliters, you would have 90 milliliters of the alcohol and 10 milliliters of water. That's a 90%. So it's 90 out of 100 total. 90 are alcohol out of 100 total. So a lot of our that's a concentration of that alcohol. A lot of our concentrations are in percentages. And some of them are in mass per volume. So you can have a percentage that's, for instance, 10 grams per 100 milliliters. So then you can give that concentration. There's 10 grams per 100 milliliters, and you can do the math, and that would be, what would it be, 0.1%? I can't do math right now in my head. No, it'd just be 10%. I'm an idiot. It'd be 10% mass volume. Here, though, we're saying it's this many milliequivalents, which you could go back and do the calculation backwards, which I'm not going to ask you to do, but you could go backwards and say a 154 milliequivalent per liter solution, then I could convert that to 1,000 milliequivalents equals 1 equivalent, and then I could go backwards to figure out that's 1 mole is 1 equivalent. 1 mole of sodium is 1 equivalent, and 1 mole is 22.99 grams. Do you follow what I'm doing? I see your confusion. I see your confusion, okay? You're thinking really deeply, which is good. You're not going to have to go that deep, okay? But that's a good question. All right, the next page deals with solubility. And we've already been talking about solubility, so it's a little odd to throw this in here, but it was something that I thought needed to be addressed and a little deeper. What does the term solubility mean? Well, we could say 10 things. It dissolves, right? Or you could say, well, you have to say the solubility of something. You got to be talking about something. The term solubility is and I hate to say this because I hated when my teacher told me this, it's relative. The term solubility is a term that describes something compared to something else, basically. And I'm going to write it down and we'll talk about it and you'll get what I'm talking about, okay? The amount of solute dissolved in a given amount of solvent under specified conditions. The amount of solute dissolved in a given amount of solvent under specified conditions. Solubility of substances is given on solubility tables or charts. And helps in determining the amount of solute that will dissolve under conditions, and I'm going to put conditions in quotes. And again, this is a lot more writing than probably needs to be to understand it. I think the best way to explain it is to look at an example. Table sugar, which is sucrose, okay? I'm going to give you the solubility of table sugar. And if you look at what I've said, solubility is the amount of solute that's dissolved in a given amount of solvent under certain conditions. That's what I'm going to show you. Table sugar, 204 grams, will dissolve in 100 milliliters of water at 20 degrees Celsius. That is the solubility of sugar. Now, let's get this in perspective. There's a table. There's lots of tables. Could be a graph. It could be an actual table that shows numbers. Regardless how you find it, you can find them all over the internet. You can find them in books. There's all kinds of solubility tables. So you could go to the solubility table and you're going to find information similar to this. So what does this mean? This means that if I have 100 milliliters of water, now I have no water left, but I know about, if I drew a line right around the bottom of this, and that was with water, that's about 100 milliliters of water, okay? Is that much water? No, not much water, okay? Do you remember what a pound is? How many grams? 454 grams, okay. 204 grams of sugar, white table sugar, will dissolve in that amount of water, 100 milliliters of water, in a room a little cooler than this room. Does that, whoa, nobody has that thought? Almost half a pound? You follow what I'm saying? You may not believe that. It's the truth. That's the solubility of sugar. The point is the solubility of sugar is sugar soluble? Pretty soluble? It's very soluble, isn't it? It's very soluble. In other words, basically what that's saying is 204 grams of sugar will dissolve in 100 milliliters of water at 20 degrees Celsius. Now, what do you all know happens when you heat the water up with sugar? It'll dissolve quicker and more will dissolve, won't it? Have any of you ever tried to make rock candy? It's hard to make. But if you've ever successfully made rock candy, what did you have to do? You had to add more than 204 grams per 100 milliliters and then cool it down and then hope it crystallizes out onto your stick. All of these have special words that we call them: saturated, unsaturated, and supersaturated. Saturated, the saturated solution is what the solubility tables are telling us. They're saying to make a saturated solution of sugar, water, 204 grams of sugar will dissolve in 100 milliliters of water at 20 degrees Celsius. That's a saturated solution. Now, what would an unsaturated solution be in relative terms? I haven't written this down, but can we common sense say what unsaturated would be? If 204 grams is saturated, what would unsaturated be? Thank you. Less than that. Does that make sense? What would supersaturated be? More than that. Okay? So let's write the terms down. Unsaturated is less dissolved solute than could be dissolved in the solution. Less dissolved solute than could be dissolved in the solution. Saturated is the maximum amount of solute is dissolved. And I'm going to make a note, solubility table gives that information. And then supersaturated is more solute is dissolved in the solution due to solution being heated, then cooled slowly. So supersaturated is more solute is dissolved in the solution due to solution being heated, then cooled slowly. In the wintertime, there sometimes is a kiosk in the mall that sells a supersaturated solution as a hand warmer. Anybody know what I'm talking about? Sam's also sometimes has a little person in there pawning those. Do you know what I'm talking about? Anybody seen them? Tell me what you've seen. She's exactly right. Anybody know what we're talking about? They're little plastic bags. It's a real thick plastic bag. It's not like a Ziploc bag. It's thick plastic, and it has a clear, colorless solution in there. It looks like water. I mean, you wouldn't know any different if you didn't know, if you didn't read it. But it's clear, colorless, and there's a little metal disc about the size of a penny, but it clicks. You know how like a pickle jar clicks? I don't know what that would be called. It just clicks. And so what happens is inside that bag, you've got that little disc, and what is inside of that bag is actually a supersaturated sodium acetate solution. And when you flick that disc, that gives it enough activation energy to crystallize out, and when it crystallizes out, it actually gives off heat. And the really cool thing about those bags is they're reusable, because what can you do? You boil it to put it back into solution, and you reuse it again. And you can just keep using it over and over and over again. It's really cool. You have seen, if you've ever seen or eaten rock candy, same scenario. The problem that I've had with making rock candy, has anybody tried making rock candy? Did you do it successfully? Really? That's awesome that you were able to do it. Did you do it on a stick or string, or do you remember? A string. Every time I've tried to make it, I get basically a jar full of crystals and it won't just crystallize on the string. Were you able to do yours? Yeah, that's awesome. Because what you have to do with that is you have to basically make a really, really super saturated solution of sugar water, which is like a syrup, but you cannot let it cool quickly. You couldn't like just put it in the freezer to cool. You have to let it cool slowly. Then while you've got that syrupy solution, that's when you stick the string in, and ideally it will start to crystallize on that string or the stick. But it's hard to do. Now there's a natural substance that's also supersaturated that many of you like to eat. Anybody know what a natural solution is that's supersaturated? It's a natural sugar, honey. Have you ever had a honey jar that you didn't eat all of it and then you left it for a while and you came back and it's like crystallized? What is that? A supersaturated solution. Do you know how to get that back into liquid? Heat it up. Yeah, and it puts it back into solution for you. So, honey is supersaturated. The next thing we've actually already talked about a little bit, so I'm not going to spend a whole lot of time on this, but I'm imagining some of you don't remember. Go back in your notes or in your mind. Do you remember intermolecular forces? Anybody remember that? And do anybody remember what they are? Say them. London dispersion forces, dipole-dipole, and hydrogen bonding. And when I talked about those, I told you we're going to talk more about them later, but I said all molecular compounds have London dispersion forces. If you have a great difference in electronegativity, meaning you've got a polar bond, you have dipole-dipole. And if you have hydrogen bonding, what do you have to have present? Hydrogen, oxygen, hydrogen, there were three, hydrogen, oxygen, hydrogen, nitrogen, and hydrogen fluorine. So if you have an HF, an HO, or an HN, then you could have hydrogen bonding. And I believe there was a small little note that said intermolecular forces will affect solubility and boiling point. I think that was on that page. Well, we're here now. We're with solubility. And the term like dissolves like means if you have a substance that's like another substance, and I am fairly certain I mentioned this. Didn't I mention this when we were talking about polar and nonpolar molecules? I thought we did. Okay, so what's polar? Tell me who's polar? Water is polar, right? Water is a polar substance, and water is a universal solvent, meaning everything is always tested in water. If you don't know what it is, you test it in water. Because if it's soluble in water, then that says it's got either hydrogen bonding occurring or it's a polar substance. That's what we always do if we don't know what we have. We want to test it in water. So it tells us that ionic and polar covalent compounds are soluble in water because water is a polar solvent. Water-soluble compounds are ionic compounds, will be water-soluble usually, or small polar molecules that can hydrogen bond with the water solvent. And then I'll remind you what hydrogen bonding is. Water solubility for molecules or covalent compounds can occur with small polar molecules or those that have the many oxygen or nitrogen atoms that can hydrogen bond with water. Nonpolar compounds are soluble in nonpolar solvents. And that's why we talked about oil and water don't mix, but oil-based paint can be cleaned up with diesel fuel. Why? Because they're both what? Nonpolar. I'm pretty sure we talked quite a bit about this. Am I right? I thought we did. Okay. The term solvation, I want to mention the solvation. This is actually, I'll be very honest with you. That word solvation was actually kind of a new word for me when I started teaching this class. And I'm like, I don't ever remember talking about solvation before. I'm like, why do we have to worry about that? Well, then something happened, made me realize. So it's kind of a funny thing. What is it, first of all? What is it? It's the process of surrounding the particles of solute with solvent to enable dissolving. The process of surrounding particles of solute with solvent to enable dissolving. So, tell you a little story, and I'll try to make it quick for us. Had a diesel fuel tank on a little lawnmower tractor. It was leaking. It's leaking diesel fuel. So my husband, who is a retired firefighter, said to me, get a wax ring. Now I'm telling you all stuff you probably have no idea what I'm talking about, so I have to explain a little bit about this. Does anybody know what a wax ring is? That's what I thought. A wax ring is what's underneath the toilet. Real quick plumbing lesson. You have a pipe coming out of the floor that's usually a 4-inch or 3-inch pipe, and that's the main poop line, for lack of a better word, okay? That's the main septic or sewer line. That's all your wastewater goes into this big pipe. A toilet does have a hole in it, right? You've seen that hole, you clean it. You know what I'm talking about? The hole in the bottom of the toilet? Okay, that usually has a loop in it, and then it goes down and there's a hole. If you pick up a toilet, which don't do that, but if you picked up a toilet, you'd see there was a hole at the bottom of your toilet. The pipe that's coming out of the floor has a wax ring around it, because what do wax and water not do? They don't mix. And so basically the wax ring is there to seal that area and hold, and it doesn't hold the toilet. The toilet's got bolts on it. That didn't hold it. But it basically seals off so no water can come out, no smells can come out, and it just is an extra seal. That's what a wax ring is. So wax ring, it's useful for lots of things. It's just a good wax. It's just wax is what it is. And so my husband says to me, take a wax ring and rub it on the where you think the leak is on the fuel tank. Me being the chemist that I thought I am or think I am, argue with him. You can't use a wax ring. Wax and diesel fuel are both nonpolar. The diesel fuel is going to dissolve it. I know what I'm talking about, you know? I mean, that's what I'm thinking. Because I am right. They're both nonpolar, right? And like dissolves like, right? He says it will work. It's what we used to use when we went out on a wreck and there was fuel leaking out of the gas tank of a car. They would carry wax rings on the fire truck and they would coat where the hole was, and that would keep the gas from coming on out of the car to get it to the junkyard or wherever the car was being towed to. It'll work. I don't believe you. It'll work. Okay, I did it. It worked. And it made me mad because I'm like, that doesn't make sense. They're both nonpolar. There's no way. Now, think about that for a minute. What does dissolving really take? Now, go other routes of your own world. You put your sugar in your tea. What do you do usually? Have you ever put sugar and not stir it up, and then at the end there's like this pile of sugar down the bottom, and you know sugar's soluble in water or sugar soluble in tea? Why didn't it dissolve? Did it get solvated? I never really thought that, I just didn't realize this really was something that had to happen. But when you stir, you're solvating, basically. The particles are being solvated. So why did the wax not break down? It's really cool, because when you think about it, here's what's going on. Imagine, if you will, there's a hole in this jar. And if I fill this hole with wax, and then I put diesel fuel in the jar, how much of that wax is actually being exposed to the diesel fuel? Not much at all. And so is the wax being solvated? No. Now, if I were to take a little piece of wax, put it in here and stir, and break it up, would it finally break down and dissolve in it? Yes. But that's why it works. It still hadn't leaked. It still works, and that's been 2 summers ago. So it works. Isn't that wild, though? That's pretty interesting. Solvation is something that really is real. I didn't think it was real, but it really is real. It's something really going on. So it takes the process of surrounding the particles with a solvent to help with the dissolving, which is why stirring, that's why we stir things. All right, real quick, tell me about the water solubility of each of these. Based on what we've talked about in the past and tonight, potassium chloride, will it be soluble in water? Why? It is what? Is it an ionic compound? And it's polar, yes. It is ionic. Good. So KCl is ionic, so it's going to be soluble in water. What about methanol? And I've told you what it is. It's CH3OH. It's a small molecular compound, but what does it have going on one end? What do you see? So what does OH allow for? Hydrogen bonding. Go up a step here. Nonpolar compounds are soluble in nonpolar solvents, yes, but go up one more. Water solubility for molecules occurs only with what? Small polar molecules, or those with the ability to what? Is this small? Now, some of you don't have a clue what this looks like, and I understand. I haven't taught this to you, but here. Now, does that make it look a little different? This C is bonded to the 3 H's, and it's also bonded to the OH. This is small. This will dissolve in water. Methanol will dissolve in water because of hydrogen bonding. So it will be soluble due to hydrogen bonding. Now what about hexane? It's straight up carbon and hydrogen. You think it'll be soluble? No. Is it all molecular? Is there anything there that possibly could be polar? What's the carbon-hydrogen bond? Do you remember that? The difference in electronegativity is not great, so that means it's what? Non-polar, which means it will not dissolve in water because it's non-polar. So it is insoluble. Insoluble, non-polar. Insoluble, non-polar. These compounds at the bottom, two different compounds, and it's a good thing to look at these because we're going to start seeing a lot of this after Halloween. After the test 4, you're going to see a lot of this, okay? The molecule at the top is stearic acid, and it already gives you the fact that it's water insoluble, but I want to talk about what you're seeing here also. This is a Lewis structure. That's what you could draw. This is a ball and stick model. You're not going to draw ball and stick models. These are the same. Some people like to see this better. Some people like to see this better. The point is in showing you the structure. What is all of this area? Polar or nonpolar? It's all nonpolar. Is that all nonpolar? What is all of that? Carbon bonded to carbon or carbon bonded to hydrogen. So this is a huge nonpolar section. Sure, it's got a little polar bond down here. Sure, it's got hydrogen bonding down here, but who's more powerful? That huge nonpolar section. And it tells you most of the molecule is nonpolar, so it is not attracted to a polar solvent like water. So it is insoluble. Insoluble in water. Glucose. Guys, glucose is soluble in water. That's your brain food. And what are you mainly made up of? Water. So we're glad glucose is soluble in water. Glucose is soluble in water, but let's talk about why. Because look at glucose. What is glucose? I'm going to show you. It's C6H12O6. That's glucose. Now, if I just wrote C6H12O6, would you know it's soluble in water? No, you wouldn't really know at all. But then when you see the structure, tell me now how you know it's soluble in water. What does it have a lot of? Do you see all those OHs? And what does OH do? Hydrogen bonding. And so it is soluble, and it tells you down here, many OH bonds for hydrogen bonding to water. And so it is soluble in water. Go ahead.
So is it only the OH that we consider it soluble?
No, it could be HN or it could be HF, but OH is the most common. OH is the most common. And to be honest with you, as we get into, after that 4th test is all, we go into that organic set. Well, we do nuclear, then we go into organic, and we're almost always going to be looking at the OH to see if it's going to be soluble or not. So OH is one of the most common ones. All right, the last thing we want to look at is the effects of temperature and pressure on solubility. Again, so much of this is information that you already knew. You just might not have known you knew it. I want to go back to that solubility table I mentioned earlier. How would somebody create a solubility table? Have you thought about that or figured that out? How would they create a solubility table? Do you know? Say it again. That's exactly right. I mean, literally, think about what you're doing. You're going to have a balance. You're going to have deionized water. You're going to have probably a hot plate or a Bunsen burner. You're going to have a thermometer. And you're going to sit there with a piece of paper and good measurement techniques, and you're going to say, okay, I've got my 100 milliliters of water. I'm going to measure out sugar or whatever it is I'm trying to test in increments. Probably you start maybe with 1 gram increments, and you're going to put them in and you're going to have them stir. We luckily have a little stir bar that does it for us, and we'll let it stir. And the water, it has to stay at a certain temperature. You follow what I'm doing? And then we get to that maximum amount. We probably go over it the first time, so then we have to do it again, get that maximum amount, and we write that down. And then we say, okay, I'm going to take all new clean 100 milliliters of water up to 25 degrees Celsius. Do it again. Write it down. And what are you going to end up with? Are you going to end up with a graph? You can do that, right? So tell me what you think you would see for most solids as the temperature increases. What are you going to see? The amount of solid will what? That's going to dissolve. Increase. Can you get more sugar to dissolve in warm than you can in cold? Yes. So on your solubility table for sugar, are you going to see a line going up? It might be a curve. It may plateau off, but you're going to see definitely the lower temperatures are going to be less soluble. Sugar's less soluble, higher temperatures are more. And that's what this says. With increased temperature, the solubility of solids, what? Increases. I'm going to stick with solids for just a minute, and I'm going to come back down here to pressure, then I'll go to gases. Does pressure affect the solubility of solids? No. Think about that. Think about the solubility of solids. Does it matter if we put sugar under pressure? Do we have to put sugar under pressure to get it to dissolve? No. Do we need to heat it up to get it to dissolve better? Yes, but we don't have to put it under pressure. What do you put under pressure to get dissolved or stay dissolved? Gases. Gases. And so with increased pressure, solubility of gases, what? Increases. Increases. Let's talk about this, then I'll go back to the temperature. Tell me the real world where you see this all the time. Say it. Sodas. Tell me what you have on most of your soda containers nowadays. It's not a hard question. I may not be saying it correctly. You have a lid, don't you? Do you have a lid? How many of you buy Cokes in bottles instead of cans? Probably most of you. I don't, but most of you do probably. Why? You can put the lid back on. Does that make sense? Why does that help? Who cares if you can put the lid back on? What benefit do you have in putting the lid back on? Because you're keeping it under pressure, right? You're keeping it under pressure. That's why. Guys, when I was a little girl, we had glass bottles for Coca-Cola, Dr. Pepper, whatever. You can drink it flat, but if you want it good, you drink the whole thing when you get it, because you can put it in the refrigerator and try to save it, but it's pointless. Same things with your can. Have you ever tried to put a can in the refrigerator overnight and the next day, why bother, right? It's flat. Why is it flat? Because all the gas escaped. Now, how could you let your Coke bottle work? Why does it work? In other words, if you put it in the refrigerator and left the lid off, would it go flat too? Yes, but what do? You put the lid on. So if the gas comes out of solution, where is it going to go? In that space, right? Can it totally escape? No. Does that make sense? So that's why those are under pressure. That's why. Does anybody have one of those machines that makes soft drinks? Do you know what I'm talking about? You had one? How do they work? Tell me this.
I don't really know.
You had a CO2 cartridge though, right? So you had a CO2 cartridge, but how did you, so the thing at the top held over the bottle, and then I'm assuming there was an orifice at the there was an orifice going into the bottle itself, and then there was one with the CO2, and so it went down probably into it. Did it seal it itself, or did you quickly put the lid on? Do you remember? Don't remember? I always think those are kind of... Say it again. So it actually, okay, so the tube is down into it, so then, but you have to seal it pretty quickly. I would think, wouldn't you? Well, sure, if you drink it immediately. Is that how you are supposed to do it? Is that... Oh, it's okay. I didn't know. So it's not like you can package your own soft drinks. Oh, I didn't know that. Okay. So I thought those things, I thought you had like a bottle that you could put it in for later.
You have a lid for the bottle, but if you let it sit for long, like for that day, it would fly by the
It would be fine. Okay. Okay. So it doesn't, it's not as pressurized probably. Okay. That makes sense. Okay. Good. I've never known anybody had one of those. Okay. What about temperature though? So that's the solubility that deals with pressure for gases. What about the solubility of gases with temperature? What do you think? With increased temperature, the solubility of gases what? Increase or decrease? How many say increase? How many say decrease? How do you know? You're right. Decrease is right. How'd you know? Warm soda doesn't have as much fizz. I'm going to write one more thing, so don't put your stuff up. Let me give you a scenario if you are still iffy on this one. This is kind of an experiment you could do. If you took two soft drink bottles, put one in the refrigerator, and leave one, let's say, in a car that gets a lot of sun so the car heats up. Then take them in the house or leave, you get the one out of the car, let's say. It's been in the car and it's hot. You take it inside, you get the one out of the refrigerator, and so they're side by side, and you and your friend, both of you open them at the same time. Which one's going to let out more gas? The hot one will let out more gas. Why will it let out more gas? Because as soon as you release the pressure, because it's hot, the gas is coming out of solution. Does that make sense? And you could try it, but you should see that happen. You should see that happen. The law that we actually, I said there were no more gas laws. This is actually a gas law. But Henry's law is actually the gas law that deals with the solubility of gases. That's it. And it says the solubility of a gas in a liquid is proportional to the pressure of the gas above the liquid. The solubility of a gas in a liquid is proportional to the pressure of the gas above the liquid, which is why you put the top on to keep that pressure. So we can say increase the pressure. I'm going to leave a blank. Gas solubility. Tell me, is it up arrow or down arrow? Increase pressure, increase gas solubility. Okay? All right, bring a calculator on Monday, please, because we're going to do a lot of calculations on Monday. Have a good weekend.